Ali, go ahead.
Okay, go ahead. Give me 1 second. I'm sharing the screen. Okay. Now you can see my screen. I put it in full screen.
Yeah.
Okay.
All good.
Okay. Perfect. Great. Thank you so much, everybody. Today, the team from TC3, including Yanis, Melkor, and myself, are going to be talking about runtime fault diagnosis and reachability analysis for in-flight contingency management. That's under TC3, and our plan for the demonstration when the event is coming toward the end of the May. So a little bit about TC3 background. The goal of TC3 is to develop advanced methods for detecting different types of faults and estimating reachable regions for mission replanning at runtime for AAM vehicles. And as you can see on the top part of this image, we do have two types of fault diagnosis techniques. The continuous the signals and discrete event system fault diagnosis, and the once we detect with these two strategies for different faults, then we're going to be passing it to the next block, which is runtime reachability analysis. So our demo plan is to apply these techniques to Minihawk or Guam simulator, and then applying the diagnosis technique, and then do reachability analysis, particularly during the landing phase maneuver. So with that, I'm going to be talking about the first block, which is discrete event system-based fault diagnosis, which is using events as a sort of indication about the how the system is evolving, and based on observing the events, we try to make judgment about the status of the system and what type of fault is activated. So the case study that we are working on is that we're going to be injecting faults to a system, and the system here, what we have done, we have integrated the aileron model and the Guam simulator combined, and then once we inject a fault, then we try to use our diagnosis technique to detect the faults. I'm going to be talking about this later, but before that, let me to talk about our method that we have been developing during the last couple of years. So we do have two types of signals that we are observing. Either the signals are of discrete nature or they are continuous nature, and then we're going to be using sort of learning-based the techniques to detect events from the continuous signals. At the end of the day, what we have is a sort of discrete events. And then we're going to be passing through two techniques. Either it is a model-based fault diagnosis or learning-enabled fault diagnosis. And then the aim is to detect faults, isolate faults, and identify the type of faults. Starting with case one, where we just use a model-based fault diagnosis. We have two different signals. Some signals have either a discrete nature, or we can simply apply a thresholding, but some other faults have a more difficult nature. For example, the force signal, where the simple thresholding may not be sufficient, and we have applied a sort of machine learning technique to detect the faults. And then the aileron, whether the aileron is commanded to go up or down, or the force is pushing or pulling or neutral, and whether the aileron itself, the measure signal, is going up and down. And based on these events, we're going to be discussing whether the fault is happening or not. Talking about the mechanism, we have three lead screws, where these lead screws are converting the rotational motion of the motors to linear motion. These lead screws are connected to individual cylinders or pistons, where they push or pull ailerons, depending on the force that is generated by each of these lead screws. Here, the type of faults that we are focusing, two types of faults. The first fault that we're going to be focusing is the jamming fault, where one of the for example, pistons or is stalking and preventing preventing it to push or pull the aileron. The other type of failures that we are considering here is the power failure, where the power is cut out and the lead screw is not able to push or pull the aileron. This is a little bit more difficult to detect, because while one of the pistons may not be, one of the lead screws may not be working, the other two still are working, and then together they can still can push or pull the aileron. So this is a little bit more difficult. Now, based on all this, we have considered different types of events that you can see that we have listed them here based on different signals that we are observing. Many of these signals are we have applied different thresholds, epsilon 1, epsilon 2, or whatever. So these sorts of thresholds is saying that once passing this threshold, we can consider that an event is triggered. For example, aileron is commanded to go up. But there are some other signals that are difficult to detect them simply based on the thresholding, and we have been using a machine learning technique that I'm going to be discussing. These are what you see here. These are the observable events that we can detect them. These are the signals that we can measure, and we assume that we can measure them and we can use them in our analysis. But also there are signals that are not observable, and these have been listed as well, including false. So we assume that false themselves also are not measurable. If they are measurable, detecting the false are straightforward to detect them. But here we assume that false are not measurable. And for those the signals that are not easily detectable using thresholding mechanism, we have been using a sort of machine learning technique. We have applied different techniques, and we found that in our use case, the KNN, or for example, the regression trees are working slightly better for our use case, and that's what we have applied here. Here is after all being said, and applying different uh, uh, machine learnings and all those events and whatever, now putting all together, this is the model that we have been using when the aileron is commanded to go up. Assuming that the system receive a command, for example, the flow change, and then the motor is rotating, the force change, and then the piston is displaced, and then all those sequence of actions that are happening, and on the bottom you can see a more kind of abstract model of it. So each of these, to make it easier to discuss and represent it, each of these events are represented with a symbol. So what you can see on the bottom is a model when the aileron goes up, but also that's what you can see here on the right side, the complete model. So the complete model, on the center, you can see the normal behavior of the system, where the left part is when the aileron goes up, and the right part is when the aileron goes down. And then the two orange and red parts are the faulty paths that the system may go, depending on whether we do have jamming faults or power failure. And then, having this model, we have built a diagnoser. What you can see is basically is a sort of reachability analysis on the discrete events and the states of the system. And we say that, okay, for example, initially we are in normal mode, and then if an event A happens, potentially what states we are going to be. And as other events are observed, our guesstimate is narrowed down to a better and better estimation where the system is located. So based on the sequence of events, we are able to narrow down our estimate and say that what the state the system is, and what fault is activated. And know that some of the events that you can see on the left side are not observable. That makes it a little bit more challenging. So understanding that some events on the left side of on the model is not observable, how the diagnoser can detect the fault. So that's the system that we have been working. And if you want to see how these two systems are working, on the left side you can see the system, and on and then on the right side what you can see is the diagnoser, and these two are working synchronously. And then this is the synchronous operation of the system and the diagnoser. We have other works that we have been discussing the challenges of synchronization and what happens if the synchronization is not perfect and we are missing some observations and so on. But here in this slide, what you can see is a perfect synchronization of the system and the diagnoser. Initially, the system is normal and it goes through a sequence of events. Upon observing an event under the system, the diagnoser evolves as well. And then, for example, after observing event H, and then event MI, and then this is a normal operation of the system when the aileron goes off, and then the system, the diagnoser, as observes the event, goes transits as well, and finally goes back. So this was a normal cycle. But then, what if the situation that, for example, the event A happens, that the diagnoser transit to a new state here, and then imagine that at this stage an event faulty happens. So the diagnoser initially doesn't notice it because F is an unobservable event. And then after moving to the next state, again, that is also an unobservable event, so the diagnoser does not move. And then the event N happens, and then the diagnoser transit to a new state, and it's saying that looks like that if a fault F2 has happened, and the system looks like to be in either a state 19 or 20, and then eventually after observing the event E, the diagnoser will say that, okay, now I can say that the system is in the state 21 and the fault F2 has happened. So that's the way that the diagnoser is working synchronous with observation of the system. So so far what you saw, we have been only focusing on the aileron, but the reality here is that on the top of those observations, we can also have some observation about the flight maneuver information. For example, whether the system is whether the aircraft is rolling or banking or whatever. So that sort of information also is incorporated, and then we have expanded the observation of the system to be able to expand our observation, and then expanding those event set that we do have, and bringing what I say here. So far, we were focusing on the local information. If we consider local is the aileron, now we also have a sort of global information. And global information, I mean the behavior, about the general behavior of the aircraft. That's what I refer to global behavior. And those are additional events that we have added to our event set. And then given that this is a new model of the system, where the system banking to the right, banking to the left, or level position, and different operations that you can see. Pretty following similar concepts, we have developed a new diagnoser here for this system that is evolving as well, and the same mechanism is applied here as well. But here is the case: as the states of the system are increasing, this is the states of the observer also increasing, and a little bit bad news is that this whole process is exponentially expensive for building the diagnoser. So given that, we also explored another strategy, which is a slightly less expensive in terms of computation side of it, and then added the diagnoser using a simple the neural network. So in that sense, we went through the whole process of the generating data, then labeling data, and then training the system, and ended up with a diagnoser which is basically a neural network with 3 layers, and the hidden layer here, for example, has 14 neurons, and then pretty kind of manageable computation that we do have here as well. And here's again, it's working in that sense. Now we don't have a diagnoser the way that we had it before. It's just replaced with a neural network, and what you can see again, it observes the events, and after observing the events, the diagnoser says that what the state the system is located, and then after observing the events, it's able to say what state the system is, what mode the system is, and finally guess what if a fault has happened or not. Also, now to put all these together, we have developed a simulation environment that uses the Guam model, but also incorporate the actuator model as well, and then combine them together, and then visualize them using the flight here. And here is the simulation that we have developed. The results, by the way, was presented in one of the conferences last year. This is the simulation environment that we have been discussing, and that brings the aileron and the Guam simulator, and all together visualized through a flight gear. So what you're going to be seeing basically during the demonstration in May is that presenting all these three techniques in this simulator of whether it is model-based or learning-based, and whether to have the global information or know just the fault, just the event information about the aileron, and all this information will be presented during that day. So that was the information about our side. If you do have questions, I can answer now. If not, I'm gonna passing it to Jens.
Thanks, Ali. Let's see if no questions.
Ali, actually, I have a very quick question. You mentioned, unless I misunderstood you, you mentioned that you were looking at applying either model-based or machine learning, depending on a fault. Why not apply both and then A as a one checking the other, and for the second reason, you can compare performance and applicability to the same fault.
That's a good idea. We have applied both of them already. We are in the middle of and wrapping up both methods. Yeah, and we can compare both. So hopefully during the demo date, we can compare the two methods and explain that. Alternatively, I think what I get from your suggestion is that also to have them running concurrently, and that's alternative strategy as well. But at least the minimum that what we can do during the demo day to compare these two methods of model-based and neural network-based and see which one is operating kind of better. Simply what I can say is that the neural network-based is more computationally manageable compared to the exponential complexity of the DAS-based model. But as far as performance, I think they might be more or less the same. I would rather to then compare them a little bit more through with the team and then get back to you to say about the comparison of these two methods.
So yeah, and if it's computationally not feasible to do it in the actual vehicle, you may want to try to do this in your simulation. And I'm thinking more from the robustness resilience perspective, right? You never want to have a single point failure algorithm. And so if you're running dissimilar algorithms to identify the same thing, then you have a little bit of that robustness built into the system.
Exactly, yeah.
That's what I'm thinking. Okay, thank you.
Great, thank you. And I believe the two people, one student, Asmul and Milot, which presumably they are also in the talk, and hopefully they heard the comment and we can continue discussing with them as well. And I wanted to just acknowledge their contribution to this, and we're going to be working with them, and they're going to be there during the demo and present and discussing the details in more details during the demo day. But thank you so much.
Go ahead, Yanis.
I'm not sure he hears us.
He's muted. Yanis, you're muted.
Yeah, guys, I can hear you. Give me 1 second because I think I'm messing up with swap. Come on. Now.
It's good now on our side. Now it's on.
Okay.
Yeah, it's good.
How about now? Okay. Hope you guys can hear me.
Yeah,
we do.
Okay, folks, I'm going to present our demonstration plan, which is in collaboration with Melchior. So a little bit of an overview of what we're trying to do is it's pretty much covered. This was a standard slide that we've used in the past. What is the idea? The idea is to be able and identify faults. This is our part, and then Melchior is going to explain his methodology, which is about fault tolerance, like reachability analysis, with something between prognosis and fault tolerance, if I describe it correctly. So the platform of platform of choice is going to be, after a lot of deliberation and for many reasons that I'm going to try to explain, it's the Minihawk VTOL simulator, which has been developed in collaboration, I believe, with UNR, and Urbana-Champaign. The research objective is, at least from our perspective, is to design an algorithm that's going to be able to detect a rotor malfunction, specifically the rear rotor of the tricopter, using input and output data and the aircraft's mathematical model. So the test scenario is going to be the Minihawk operating in vertical takeoff and landing mode, and during takeoff there is a fault that's going to take place, which is essentially is going to degrade the performance of one of the rear rotor, and then we're gonna, the task is to be able and identify it. So a little bit of the architecture of the simulator. Now, there is the symbiosis of three components. It is ROS, ArduPilot, and Gazebo. Gazebo is the physics engine and the visualization tool. ROS has to do mostly with message passaging between Gazebo and the heart of the decision making. The microcontroller is ArduPilot. Now, luckily, we are able to add MATLAB into the mix, which is very convenient for us because we feel comfortable in writing in algorithms in MATLAB. So a little bit about the architecture of the ArduPilot. Now, if you have played around with that, it's pretty much chaotic. And Vincent, my graduate student, Vincent Wow, put some considerable effort and be able and chart the different subroutines and modalities that are taking place to the Ardocopter. And the reason was we're trying to figure out a way that we can plant and we can seed a fault into the system. And we managed to find, with the help of Pratiko Aurora from UNR, we managed to identify a function, pretty much a routine, where the rotors are operated. And at this routine, we seeded the fault, which has to do with degrading performance of the rear rotor. So the fault injection is taking place in the ArduPilot. In other words, we're having a video here that shows what's going on. I mean, initially, the Minihawk is taking off, is reaching a reference altitude, and then the fault is injected. I mean, you can see gradually this is the faulty operation. Now, what's happening is that because of loss of degrading power in the rear rotor, you're having those pitching moments being created, and at the same time, the controller is trying to compensate for this. Fault. Now we record the input and output data. The plan is to derive our own model with the help of Melchior and his team to derive a dynamic model, and based on the input output data and the dynamic model, develop our algorithms. So it's the fault, just to give you a little bit of block diagrammatic representation of how the fault is seeded. Well, the commands, the reference commands, and also the state of the system goes to the controller. The controller outputs thrust. The problem is that the thrust that you are out, like the desired thrust that you require, never reaches the actual motor because the motor doesn't perform the way it should. So again, there's going to be some sort of degrading performance, which is gonna give us the signature signals to be able and identifying the faults. So this is how the block diagram, like this is a little bit about the configuration of the tricopter. As you can see, all of the rotors are pointing upwards. There is a typo, the rear thrust is denoted by T3. This is where the degrading performance it's going to take place. So we're having the quadrotor dynamics that we're going to need to identify for our application with a certain fidelity. And then there is, and then on top of that, we're going to have our fault diagnosis technique being built in. So pretty much, I'm going to spend a little bit of time to describe what we are trying to do and why we believe this is a useful contribution. Well, typically, I mean, this is something that we have described in the past. Our approach has to do with trying to harness the benefit of discrete event systems, and also taking also into advantage the analytical tools that continuous valued dynamical systems offer. So the way to go, I mean, if you want to build a bridge between continuous value dynamical systems and discrete event systems, according to our opinion, is to have a hybrid sort of systems. In other words, systems that have continuous valued dynamics, and they have different modes of operation and the transition between these modes. So pretty much the way that our algorithm works, we're having some sort of a model, sensor measurements. The algorithm is executing in the autopilot, and you're getting a probabilistic measure of whether or not a fault occurs. So we're talking about change detection. In other words, systems for which their dynamics are subjected into changes. Those changes may be abrupt or incipient in our formulation. So in the discrete event methods, and especially if you are dealing with fault spaces, high dimensional fault spaces, and if you take into account faults that are occurring at the same time, the dimension of the problem becomes really big. I mean, it's becoming really complex. So we were trying to find a very computational, efficient, and elegant way of being able and embed, fuse, if you like, multiple modes of operation into a single state. Okay, and this is going to give us a tremendous computational advantage when it's about real-time implementation. So what's happening is that we introduce those binary states, which are practically a hidden jump Markov model. It's a binary state that jumps from 0 to 1, and from its expected value, we can get a confidence metric of whether or not the fault occurs. This state is embedded within this hidden Markov model is embedded within the dynamics of our system. And every time this mode transition can let us know if a fault occurs or not. So now the detection and identification problem, in other words, not only figuring out if a fault occurs or not, but pinpointing this fault, becomes a standard estimation problem. Now, the the filter that is capable of providing design flexibility to account for these systems with discontinuous dynamics, and at the same time having multiple states and perhaps non-Gaussian noise is the particle filtering. So I'm taking one of the standard examples of a function that of a dynamical system that you can find in the literature, and so how these binary states jump by observing, by collecting observations of the system's state. So what you can see over here is the transitions of the population of the particles from the healthy mode to the faulty mode when the fault actually occurs. And by taking the expected value of these binary states, I can get some sort of confidence of whether the fault has occurred or not. Now, where this algorithm is going to reside is going to be having this symbiotic relationship, as I mentioned before, with the autonomous controller, or it can also be executed on the edge of the sensor, where the data are collected. Pretty much the idea is that the output of this algorithm is going to provide some sort of decision-making. It's going to assist the decision-making of what is the next action. Here's a student who did all of this nice work. This is Vincent, and our work has been funded by NASA and the UIUC award. So I think I'm on time.
Thanks, Yanis. Questions for Yanis?
Hi, can you hear me?
Yes, indeed.
I just had one question. How would it differentiate between a fault and a disturbance in the current setting? For example, a turbulence versus, an actual fault in the power system.
Yeah. So in the realm, in the literature of fault diagnosis, those are two different categories of faults. What you are describing is the presence of an exogenous signal. Typically, there is a different treatment when you having to deal with this category of faults. This is not something that's been taken care of, what you see over here, unless it is appropriately modeled. In other words, you know what is this disturbance is going to be. What we are predominantly dealing is what is referred to as a temporal change detection. At some point in time, something changes, and you have to figure out what is that. So I'm not sure.
Okay.
Yeah, I'm not sure if that covers your question.
Okay, no worries. Thanks.
Thank you.
More questions?
Yeah, I have a question. This is Andy Provenza at
Hey, Andy.
NASA Glen. Hi. So I'm thinking in terms of the demonstration that unfortunately I won't be able to attend, but I could see this Arducopter taking off, and then you would actually create a fault in that third back end rotor, essentially maybe shut it off. And then you mentioned a reduction in capability, and then the controller somehow taking over. I'm guessing since the front two rotors can produce thrust, maybe not as much as the three together now. And then there's a moment around the center of mass of the vehicle due to those two front thrusters. I assume then maybe there's the control surfaces on the back end that can compensate. So would I see that? Would I see the plane hover, the rotor turn off, the plane kind of do some dynamic motion as a result of the loss of that rotor, and then some corrected control authority to put it back into hover? Is that what I would see?
So, Andy, the thing is that there is not a backup plan. What do I mean about that? You are correct about the first part, that the two rotors are going to be operating normally, but there's going to be loss of effectiveness in the rear one, right? So
Yeah.
what's going to happen if for example, the rear rotor is cut off completely, essentially you're going to create a moment from the first, like a pitching moment from the front ones
Right.
completely, and you're just going to roll. So so the injecting faults in aircrafts, and especially if they're having very high moment to inertia ratios, which are practically very agile, they have to be very delicate in the case that the controller can handle them. If it's a critical malfunction, in other words, you cut completely the power, I mean, immediately you crash. At this point, fault diagnosis becomes pretty much meaningless. There is not enough time to compensate.
Yeah. I see. Yeah,
So,
the inertia is so low. So you're
yeah,
gonna just reduce the functionality of that rear
yeah.
rotor then. Yeah. Okay, I see.
Yeah.
Okay.
So, I mean, just to give the practical scenarios that you deploy some sort of this UAV, or for example, you're having this automated aircraft that's operating for commercial applications. It doesn't experience a critical failure, but doesn't fly as it's supposed to fly. And suddenly, you're having this button beeping at the end of this supervisor somewhere remotely that tells you, no, this doesn't work the way it's supposed to work.
Yeah. Yeah, I see now. Thank you for that
Thank you.
answer. Yeah.
More
Okay.
questions?
So if I may just make a quick comment to Andy, one of the things that it's happening in TC3, and they're demonstrating a very particular technology that's not necessarily tied to a controller that can compensate for the fault. They're demonstrating fault detection and identification.
Mm-hmm.
Melchior, unless you're going to talk about a control compensation, I don't want to.
I will not.
Right. So being able to understand how well or poorly you can define or understand what the fault is, I think is important. But then in a grander scheme of things, it's going to get implemented into a system that actually has control compensation that can take care of a lot of the faults to the physical ability of the vehicle. But again, it is still something you want to be able to understand because that will have implications for other mission type of variables in considerations.
Yeah, thank you.
Okay.
Yeah, that makes complete sense. There's, you've got to be able to detect the faults well to then control the change in the dynamics. Yeah.
So yes and no. You can control change in the dynamics without truly understanding the physics behind the fault. L1 adaptive control comes to mind. It can take care of that. However, what you want to do is for your mission performance, you really want to understand what the fault is, because then that would have implications on your achievable future mission conditions. And I think Melchior is going to talk a little bit about that.
That's right.
Part of his reachability. So it has implications beyond just immediate control.
Okay.
All right. Sorry. Thank you.
Thank you.
Thanks, everyone. So, Melchior, are you taking over already? If no more
Yes, I
questions?
am. Thank you.
you.
In the past 5 minutes, as Yanis was talking, the internet where I am died. So now I'm on my phone's internet, and I hope that everything survives. But I'm trying to keep an eye on whether everyone's picture becomes frozen for me. Thank you. Thank you, Yanis. Thank you, Irene, for this kind of introduction. You kind of spoiled the first few slides of what I'll be talking about, but I think that it provides exactly the right connection between what Yanis is doing and what other TCs are doing, which is this kind of control design. And so everything you said, Irene, is exactly correct. What my part of TC3 is interested in is getting some, I wouldn't call it yet mission level, but getting an understanding of once something bad happens, how does this affect the system? And I don't necessarily, for myself, care exactly what the fault is. I just care about some features of that fault that help me inform what is the system capable of doing. And then, of course, ultimately we want to compensate, and we want to say, hey, your original task is impossible to satisfy anymore. Now go find a different task. So I'm interested in certifiable capabilities. And what I mean by that is really once a fault occurs, there are three things that we can still draw from, or four things, four pieces of data that we can still draw from to kind of estimate what the system is capable of doing. One is partially imperfectly observed past current trajectory, simply sensing. One is the nominal transition model of the original system without the fault. And this is something that our TC is not interested necessarily in developing. This is something that is given to us by, let's say, TC4. I'm also interested in learning what is preserved by default. And so by that, I mean, in very vague sense here, some sort of design knowledge, some sort of physical laws that get preserved by default. Now, for that part, fault identification becomes more important to me, because if I don't know much about the structure, the less I will be able to guarantee about this partial knowledge of this new transition model that I have. And so once I'm armed with the partial new transition model, I want to develop and I'm emphasizing here, a conservative estimate of completable tasks, by which I mean, I don't want to have false negatives. I want to be able to say, hey, I guarantee you that the system is able to do at least this. And then ultimately we want to provably learn online how to complete a task, and over time ideally get less conservative, and that gets closer to the L1 adaptive control and to the kind of other control compensation methods. So what I mean by unknown dynamics or partially novel transition model is something along the lines of x dot equals f question mark xu, where this question mark is an unknown function. And what I mean by that is that this could be a significant change of at least quantitatively, numerically, it can be a significant change from the original dynamics. It could be that it is not a small disturbance. It is not necessarily even finitely many parameters. It could be a substantially different thing. Of course, this is not particularly new, the idea of trying to deal with unknown dynamics, and robust control does it, kind of classical methods of adaptive control do it. However, both assume that the original target remains reachable. And so that poses limitations. In particular, I have a video that I love showing, and I hope it'll show. These are of course not UAVs, but the vehicle that got hit, whatever its original target was, it is at the very least doubtful whether it can still reach its original target. And so we're interested in figuring out what this vehicle can do. So after a fault, after a change in dynamics, the system can almost certainly not use the same control law to reach its target. It might not even be able to reach its target, especially kind of long term, using any control law. So there needs to be some sort of a higher level decision making that will say, hey, I don't have hope anymore, or I don't think that I can reach my original target anymore. Let me figure out something else. Let me figure out whether I can at least land safely. So we're really interested in what is the vehicle certifiably capable of doing, even if we don't yet know how. And I'm not going to get into this part of how to do it. How to do it is a part that, of course, L1 does amazingly, and other control methods as well. So in terms of what is certifiably capable of doing, if nothing is known about the system post fault or post disaster, nothing is certain. We can't guarantee anything. However, if we do have some knowledge about the remaining system dynamics, then I can look at the set of all the dynamics consistent with this current knowledge. So all the possible post-fault dynamics, I can put them in this set dcon. I can compute the reachable sets for every possible dynamics that now represents the ground truth, and I can intersect all of those reachable sets. If you are in the intersection of all of these reachable sets, that means that no matter what the ground truth is, as long as it is in this set dcon, the state is going to be reachable. Okay, I define this. How do I compute this? This is a hard problem, and so this is, I call it classical work. It is, in a sense, the work that we've been doing over the past few years. I'm calling it classical because it is not entirely applicable to this demonstration, but it provides a good background. So one possible idea is find all the guaranteed velocities that the system can go in at a time t, and then find all the trajectories that integrate these guaranteed velocities. This will cause you to obtain at least some, if not all, guaranteed reachable states. How do I find the guaranteed velocities at time t? Well, I say these are also the velocities that I can follow at time 0, modulo maximal system wildness. And this is where things kind of start breaking down, and we start needing to adapt the theory to the real world. So I need two things. I need these initial velocities, and I need some sort of maximal system wildness. I could say something like this. The set of initially available velocities can be computed in arbitrarily short time through kind of persistent excitation. We've done that, at least in theory. A bound on the change in the set of the available velocities can be obtained from a Lipschitz bound in the possible change in system dynamics, somehow, from physical laws, from design knowledge. And so we can compute these guaranteed velocities. Turns out that this is a geometrically difficult set, but a set that can still be under-approximated in some way. And so we do that. And we figure out an under-approximation of the set of guaranteed velocities, and that gives us under-approximations of the guaranteed reachable set. So we've played with this on a simple model of a, in this case, it was an undamaged UAV. Okay, so all of these things I said hold. They are all true. However, in the real world, there are concerns about many of the pieces that I described here. First of all, I claim that originally I said the set of initially available velocities can be computed in arbitrarily short time. That is iffy. At the very least, the sensors are not perfect. There is a kind of a delay in seeing, in observing the effects of control actuation. Even worse, when I said, oh, yeah, you'll just know the Lipschitz bounds on the changes of dynamics, I may not know that. These Lipschitz bounds are something that's a mathematical construct, and it requires work to derive it from kind of physical laws. And these guarantees on reachability are only available for a short time because of the Lipschitz bounds, which allow the function to kind of get wilder and wilder over time, or reduce our knowledge of the function of the dynamics over time. However, these are three bad things, but there is one good thing. And this is a thing where Yanis and I connect very much. We can know more about this structure of the dynamics. And this is exactly what Irene was saying. If you don't care about default and you have all of these assumptions that I have, yeah, you don't care about default. But in order to get longer term guarantees, in order to get better ideas of what might be possible and what might not be possible on a kind of a task level or mission level, you want to know more about the structure of the dynamics. And that means you want to know at least something about default. And so we come back to this picture of certifiable capabilities. And this classical work that I described so far used really very little of the design knowledge and physical laws. It somehow said, yeah, there's some sort of a Lipschitz bound, and that's it. Now, with Yannis's work, we can start actually exploiting and exploring this design knowledge and fault knowledge that Yannis is developing, and the physical laws to develop more information about the partial novel transition model. And so I shamelessly stole a few of these slides from Yannis. I'm not going to go, thank you, Yannis, for your approval. I'm not going to go through them again. I just want to kind of note how all of these pieces that I mentioned before, the imperfectly partially observed past trajectory, nominal transition model, design, fault knowledge, and physical laws, where they actually come in from in this simulated scenario. So the nominal transition model comes from, explicitly or not, but it comes from the Mini-Hawk VTOL simulator. So there is some sort of real dynamics or some sort of a nominal dynamics that this simulator follows. The fault will have a particular structure. Even if we don't know this structure in advance, and this is something that Yannis will help discover, there is a particular bad thing that's going to happen. This fault generates a particular structure of the system dynamics once combined with the kind of design knowledge and physical laws. So these are all the things that Yannis and Andy described just in the question session. Finally, so I covered 3 of these things. I still need the partially observed past trajectory, and we get that from the simulator. We have the observation of the Mini-Hawk states. In this case, I think we are assuming that the states are perfectly observed, but nonetheless, I have some version of past current trajectory observations. And so now I can develop more of this structure. Yannis showed a little bit of this structure. We have really 6 options about how I might use this structure of the system. One option is, okay, assume that the dynamics are linear, perform some sort of system ID on those dynamics, and then perform reachability analysis. This is easy. I don't actually need Yannis for it. It uses no expert design physics knowledge. It is also wrong, right? The system is not linear, and in fact, the system ID does not work perfectly. Okay, so a slightly more complicated option is, okay, I will assume that this linear system is uncertain in some way, which is what I've been talking about before. So I won't just calculate the reachable set. I'll calculate the guaranteed reachable set by intersecting all of these possible ground truths. Okay, system ID is still the same. It's still easy. This is not necessarily incorrect, or this is not at all incorrect, if given reasonable uncertainty bounds. However, how am I to find these reasonable uncertainty bounds, especially since I don't have any kind of expert design physics knowledge? That remains iffy, and the guaranteed reachability computation already becomes, I wouldn't call it difficult, but it becomes non-trivial. I need to intersect many reachable sets for linear systems. Now, I shouldn't really be doing that. The next 2 options are, let me use a little bit of Yannis's model. Let me take, and this is a picture of what Yanis sent me yesterday, a linearized version of this model based on the known system structure, based on some of the physical laws. Let me perform reachability on that. This is not any harder than the original system ID was. It is still wrong because the system is still not linear. It is not as much wrong, let me put it that way. And it certainly does use expert design physics knowledge. This option 3 assumes that linear system ID works perfectly, and I'm perfectly able to generate this model. Of course, this is not true. I need some sort of uncertainty, in which case we get to option 4. System ID is still easy. This is not incorrect if given reasonable uncertainty bounds. Finding these reasonable uncertainty bounds might be a little more intuitive now, and the guaranteed reachability computation is still non-trivial. This is still not correct, ultimately. The true system is nonlinear. And so my option 5 is, okay, say the system is nonlinear, use the dynamics that Yanis developed, perform nonlinear system ID based on this known structure, perform reachability analysis. System ID is now a little more difficult because things are nonlinear. Certainly computing a reachable set becomes non-trivial because now I'm computing a reachable set of a nonlinear system. This is almost correct. What I mean by almost is, hey, nonlinear system ID is going to give you something of the right structure, but because the sensors are not perfect, because there is a delay, because fault identification is not necessarily perfect, there's still going to be some uncertainty. And so in the option 6, I really want to combine nonlinear system ID. I want to provide some uncertainty bounds where it's still a question of how to find these reasonable uncertainty bounds. But if I do that, this will be correct. And depending on uncertainty bounds, it may be more or less conservative. The price that I will pay, though, is in the guaranteed reachability computations, because now I am computing reachable sets of many nonlinear systems, and I'm intersecting those. So now we come to the question of what is actually doable on board, what is doable in real time. This is hard. Performing it through kind of Monte Carlo simulations is hard. If one performs some sort of geometrical thinking, this is to some extent handcrafted, and it is also conservative. So just as a current status, option 1 is done. Option 2 can be done. Option 3 and 5 require a system model, which Yanis has just provided us with yesterday, and then options 4 and 6 need options 3 and 5. We are performing all of this in kind of basic visualization code in MATLAB. I see that I'm coming up on the time, so let me end here, acknowledging Taha, Yiming, and Jesse, and of course our partners Yanis, Ali, Victor, Asmol, and Milad. Thank you.
Thanks, Melchior. Let's see if there are questions for Melchior.
So Melchior, help me out here. I'm a little unclear. So what exactly do you think you're going to be demonstrating in May?
So I will be providing these reachable sets, or the projections of reachable sets on some of the coordinates of interest.
And so they're going to be, how they're going to be integrated for what's being shown in flight? This is just general to the TC3 team?
Can you repeat the question maybe?
Sure. So you're going to provide reachable sets. So it's pre-trained. Here it is. I assume they can be loaded on board in some reasonable representation and code. So how are they to be used in the demonstration by the rest of the team? I mean, TC3 team.
Okay, so they are not going to be used by the rest of the TC3 team. We are the last piece in the TC3 team. They feed into us. And so we provide these reachable sets, and the idea is that then those are fed to TC1 team.
Okay, so how are you going to, I'm thinking more of check accuracy, relevance, performance is probably the better word in flight, right? So you computing things based on A, simulation, B, let's assume very uncertain models, right? That not really quote real. And now you're going to flight test things. How you going to assess performance of your reachable sets, utility of your reachable sets, etc. Right? So if I'm going to use it, how am I going to tell me?
Yeah, this is a good question, and for that I think we need to discuss with TC1. I can a simple but not ideal metric of the performance of this reachable set is me telling you how many options I'm giving you and saying, okay, this is the size of the reachable set that I can guarantee you. And hopefully the bigger the size, the more useful to you it is. Now, how that is going to be used in the actual planning of the control of TC1, I don't think that we have connected with them yet.
So let me see. I'm not getting myself across clear. Sorry. So you're going to give me options, right? So I'm assuming, assume I'm the control design or the control decision making in flight. So you gave me options. How do you use flight data and the demonstrations to assess how good or poor your options are in terms of conservatism, in terms of basically, I mean, but the whole idea is, right, is you want to provide the largest possible guaranteed operational set. Now, I understand what you're doing is conservative, granted, right? But how are you going to use actual flight tests to try to assess perhaps the level of conservatism of your options? Because I think that might give you insights into how to change or modify your theory.
Let me see if I understand the question correctly. Are you thinking of a framework in which I calculate these reachable sets kind of in advance, and then I try to modify them in some way or use them in some way during the flight testing?
Well, if that's possible, yes, but assuming it's not, how do you assess what you have provided, right? Based on the performance of other elements in the flight test. I mean, some way, how do you use the available data to reassess the performance of your part?
I'm not sure I'm entirely following. Let me try to answer. So I will provide the folks who design the controller with options. They will ideally choose one of those options. Now, it could be that the options I provided are very conservative, in which case they will never know that from a single test, because they will just choose one of the options, and that's going to be it. Now, the way that one can perform this quality control, if you will, of our method is by trying to control the system to something I'm not guaranteeing to be reachable. And if they manage to do that, that means that I'm very conservative. Does that help?
It does, and as I said, part of the question is, and part of the demo, I see not just to demo and say, hey, look, we put it in the real-time system, but it's also a way to use the data that is collected to, in a feedback loop, to improve the methods, the theory, kind of gives you something more on that, right? So that's where the question is. Okay. So potentially, right, is here's where I think is you're guaranteed. Let's try to go beyond that, whether
Yeah.
that's in a sim or in the actual vehicle, depending on the risk.
Yeah. Yeah, you're entirely right. In the sense that I think that where more and more data kind of comes in is in two parts. One part is the actual kind of system ID, but the other part is in this description of what I call the uncertainty bounds, right? Where if I get more and more data, I am able to say, hey, yeah, what I had as uncertainty bounds was really conservative. I can cut it down by half. And that's going to make the reachable set bigger.
Okay, as I said, it's just something that I'm looking for ways of trying to provide measures of performance of particular algorithms based on what happens in flight demos, if at all possible.
Yeah. Yeah, I think that's a great idea. It's it requires kind of data collection during the flight demo and then analysis after. It's not something that's kind of done in real time.
And that's fine, as long as that's part of the process and plans is where I'm heading with this. So thank you.
Yeah.
If no more questions, we can wish everyone who celebrates Easter a good Friday today and close the call. No more questions?